This. I had a student 5-6 years ago, went off to university, UT Health Science Center, nursing, and he wrote me back an email. He said, Mr. Riak, day one, he said, for about 8 hours, they just sat us down and said, you solve a problem, you're using dimensional analysis. And they taught him how to do dimensional analysis their way. They actually had forms, showed you here, you start with, here's what you've been given, here's what you need to calculate, here's how you get there.
Yeah, like anesthesiologists, they use that wrong.
Yeah, you can't get anesthetics wrong.
Yeah.
And it's usually down to very little bits of stuff, so. Okay, I started out by saying let me put these modules in context. Module 5 is something I feel you can go back and study. You can go back to those homeworks and master density, temperature conversions. All you need to do, or the thing you need to do, are problems until you feel like you got it. Module 6. I'm going to sweep through this pretty quickly and actually try to finish it today. I want you to be aware of what is a chemical reaction, why do we write things the way we do, and some basic types of chemical reactions. And then I want to, on Thursday, start the mole and Module 7. So today I'll try to get, or soon I'll try to get the Module 7 slides up there. And that is the critical one. That's the hump we got to get over to get into the rest of the stuff in this course, is the mole, molar mass, balancing chemical equations. That it's a very important module, Module 7. So if I seem to dust over this a little bit or don't dwell on it as long as you'd like to, we'll get back to some of this stuff in Module 7. All right, so we're talking about types of chemical reactions, and this is going to just break it up into some some broad types, categories. Acid-base reactions, oxidation-reduction reactions, double replacement, precipitation reactions. Well, probably we should write out a simple little chemical reaction. We've been learning some symbols. That's the element sodium. This is the element chlorine. They react to form sodium chloride. That is a chemical equation or chemical reaction. It's describing a chemical reaction. And you can see chemists aren't into a lot of words, are they? There's a ton of information in that little thing right there. We're talking about sodium, elemental sodium reacting with chlorine. Reacting with. These are reactants, starting materials. This is what we're starting with. This is the product. All right, so just kind of get some of the simple aspects of this. There's usually an arrow. There'll be an arrow, sometimes like this, which means that sodium and that chlorine is being converted into sodium chloride. It's moving in that direction. It's not particularly reversible reaction. Sometimes you will see arrows like this, which basically say, you're in a situation here where it can go to the right and form this product. The product on the right can break back down into the reactants that are on the left. And so it's a back and forth kind of a reaction. We usually talk about this as being an equilibrium situation. It's in equilibrium. This is sodium chloride. Okay, that points up one other thing. You know, I don't like to gloss over any of the obvious. Okay, it is not this. That it's tempting to write that. I got 2 chlorines on the left. Why doesn't it just produce NaCl2? The products, the reactants and the products have to be written with their proper chemical formulas. Okay? We can't change the nature of the sodium chloride just because we got a Cl2 over on the left. Follow me? And you know that it's that because that is a +1 ion and that is a -1 ion. So it forms sodium chloride, 1 sodium with 1 chloride. All right, so that's a chemical reaction. We could, and there are literally thousands of these. I mean, just to contrast it, I could take magnesium metal and I could react it with chlorine. And it's going to form magnesium chloride. What is its formula? What is the formula of magnesium chloride? MgCl2. Okay, because magnesium is sitting over here in group 2A. It is a +2 ion. Oh, look at that. It needs 2 chlorines with it. Well, that's beautiful. That's beautiful. But it doesn't always work out that way. Okay? It worked out that way because magnesium is a +2 ion. Not because chlorine is Cl2 on the left. Follow me?
So you look at the charges.
You look at the charges. You have to get these formulas right according to what is the formula for magnesium chloride. Hence Module 4, where I said chemical formulas going to be very, very critical. We can't move forward here until you can get from here to there. All right? Yes?
So the balanced equation for the first example you gave us would be 2Na plus Cl2 gives you 2NaCl.
Correct. Okay, now your name again?
Shantae.
Shantae is getting us one more step into this. This is not a balanced, this one. This top one is not a balanced equation. So we're going to get into balancing. We'll do a deep dive into balancing. But balancing means you got to have the same number of sodiums and chlorines on both sides of the equation. And like I just said, you can't do it by just changing the formula. Once you know what the formulas are, the only thing you can do is put coefficients in front. So, well, here's what's driving me here. I've got 2 Cl2s over there, so I need 2 Cl's to come out in my product. So instead of an NaCl, I'm going to produce 2 NaCl's. But oh, there's an Na attached to my Cl, right? So that is really this. It's an NaCl and another NaCl. So that gives me my 2 Cl's, but it gives me 2 sodiums. So I have to come back over here and fix it. Now it's balanced. Now it is balanced. 2 sodiums react with 1 Cl2 diatomic molecule, the Cl2, to produce 2 NaCl's. And that's why we had to write that as Cl2, because chlorine elemental chlorine exists as Cl2 molecules. And that's how we have to write hydrogen and oxygen and nitrogen and fluorine and chlorine, bromine, and iodine. What did I miss? That's about it. Hydrogen, oxygen, nitrogen, yeah. And the halogens. Those are your diatomic molecules. Okay, so that's an introduction to the chemical equation. And we will talk more about it, but now let's just kind of work with that for a minute. There's going to be these types of reactions, acid-base reactions. And what I'm going to do with each one of these is try to point out something in there that might help you identify it as an acid-base reaction or an oxidation-reduction reaction or a precipitation reaction. So let's get some examples. Acid-base reactions. I think I have a little better one. Where's my better one? There's some acids and bases. Oh, here's a good one. Here's a simple acid-base reaction. I'll move back to some of those previous slides in just a second. Here is HCl. The AQ means it's dissolved in water. It's aqueous HCl. That's hydrochloric acid. And sodium hydroxide dissolved in water. So we got a solution of sodium hydroxide. This is the acidic portion of the HCl. This is the basic portion of the sodium hydroxide. And you can see we're forming this salt, sodium chloride, and water. What is H2O? It's two H's and an O. So this H plus an OH minus makes water. So you started out with a solution of hydrochloric acid, very acidic, strong, it burned your skin. A solution of sodium hydroxide, a very strong base, it would also burn your skin. You mix them together and you get salt water. You get salt water. The water forming is reacting, neutralizing the hydrogen plus and the OH minus. So how would you recognize an acid-base reaction? Well, look for water as a product. Look for a hydrogen-containing acid and an OH-containing base. And you say, that's an acid-base reaction. So let's go look at this list of acids and bases. Well, here's acids. Here's some strong acids. Common strong acids. Notice you see an H or two on the left. HBr, that's hydrobromic acid, hydrochloric acid, hydroiodic, nitric. Remember NO3 is nitrate. That's the nitrate ion. Well, if you associate it with a hydrogen plus ion, you got nitric acid. That's nitric acid. That's a very strong acid. Perchloric acid, HClO4, sulfuric acid, actually has two hydrogens on it. Remember the sulfate ion, SO4 minus 2? Now we're putting two hydrogens on it. That's sulfuric acid. So if you see any of these in a reaction, like HNO3 plus sodium hydroxide, you say, that looks like an acid-base reaction. And that's what it is. You're going to get sodium nitrate. See how I'm figuring this out? Sodium nitrate is going to be the salt, and it's going to form water. Where's the water coming from? This plus this is forming our water. So the acid It's neutralizing the base. I'm not sure I got a slide with some bases, but strong bases. One might show up here, but strong bases. Already we've talked about sodium hydroxide, potassium hydroxide, magnesium hydroxide. Actually has 2 hydroxides on it. These are some strong bases. Lithium hydroxide. So what do you see? You see a hydroxide in there. The OH minus is basic. It raises the OH minus concentration in the water and it makes the water basic. These over here are adding hydrogen ions to the water, making it acidic. Okay, I'm not going to dwell. I think acid-base reactions are some of the easier ones to identify. Like, you've got a bunch of things to see. Yeah, I see an acid, I see a base. We will get into acids and bases deeper in, it's like module 11, I think. Our last module really gets into acids and bases. But just for right now, just kind of generally recognizing an acid-base reaction is good enough. Here's another one, and what this is showing, notice that the MgOH2, we've got 2 hydroxides here. So getting back to what Shantae was pointing out a minute ago, to balance equations, if we're going to react this with HCl, and we're going to form magnesium chloride and water, each one of these OHs, each one of these needs one of these to react with it, to form water, right? One of these will react with one of these OHs and form water. But then there's one of these left over. So really, when you get down to balancing this, we're going to need 2 HCl's, and we're going to produce 2 moles of water. Because you're going to have an OH and an OH, an H plus, an H plus. These are minuses. So each one of those is going to produce a water molecule. We're going to get 2 water molecules out of it. And it's balanced. We won't dwell any more on the balancing. You'll have activity. I'll give you some stuff. I'll give you a whole bunch of chemical equations and say balance these, work on these as a worksheet. Oxidation reduction. So let's jump over into the next category. The acid-base reaction, there's no oxidation or reduction going on. There is neutralization, but nothing is being oxidized or reduced. This one's a little bit harder to understand, but zinc over here, zinc is an element, and as a neutral element, pure zinc, it is not an ion. It's not an ion. It has no charge. Over here, the silver nitrate, the nitrate is -1, so we can tell for a couple reasons, because there's only one silver with one nitrate, that the silver is a +1, and silver is one of those that I asked you to memorize. More or less always has a +1 charge, silver. Like the halogens, lithium and those, always +1, but also silver. Why? Well, sometimes we can't answer the whys. It just turns out that's the way silver behaves right now. So it's a +1. And in this reaction, what's happening? The silver ion is becoming elemental silver. And the zinc metal is becoming a zinc ion with what charge? What charge is on this zinc right here? 2. How do you figure that out? Okay, the nitrate, there's two nitrates, and the nitrate has what charge on it? -1. There's two of them, so that is telling you that has to be a +2. So what am I saying here? The silver is going from a +1 down to 0, down, and the zinc is going from a 0 up to a +2. This is oxidation, and this is reduction. When the charge goes down, think of it as reduction. It's going down in charge, that's reduction. And what is actually going on? The zinc metal, this is what's going on. The zinc metal is being converted into zinc +2, and it's losing 2 electrons. So the zinc is losing electrons. And where are the electrons going? It's giving those electrons to the silver ion, and the silver ion is becoming silver metal. So the loss of electrons is oxidation. The gaining of electrons is reduction. All right, so that's oxidation and reduction. There's many examples of that. Where did this really name come from? Well, it came originally from stuff reacting with oxygen. Oxygen oxidizes things. So if you took iron, this is rust. This is the reaction that produces rust. What's happening here? This is 0. This is 0. These are both elements. Elemental iron, elemental oxygen. What's the charge in ferric oxide? What's the iron charge? +3. Oh, who's been teaching you guys all this stuff? All right. Pat myself on the back. Look at what you're learning, okay? You're learning this. I'm asking you questions. And what's the charge? What is the oxide ion charge? -2. So the 0 went to -2. This 0 went to +3. So the oxygen charge went down or reduced. That's reduction. So the oxygen was reduced, underwent reduction, and it oxidized the iron. The iron got oxidized. This is oxidation. And if you think about it, the iron became a +3 ion. And how did it do that? By how many electrons did it lose? 3 electrons. It lost 3 electrons. That's how it got that +3 charge. It gave up 3 of its electrons to oxygen. And 2 irons did this. This isn't balanced. We'd have to go ahead and balance it and all that sort of thing. So oxidation or reaction with oxygen is oxidation. So reactions with oxygen is oxidation. And sometimes we call it combustion. Here's the gas in your home. And when you burn natural gas in your stove or in your furnace, we just kicked our furnace on yesterday for the first time. Boom. Hey, it's a little chilly in here. Turned on our furnace. So we were burning natural gas with oxygen to form CO2 and water. This is combustion. Now, I'm not trying to confuse you, but I just want you to see that Some of these reactions might have a couple of different names. They're not contradictory to one another. When we are burning gasoline or burning propane or burning natural gas, we talk about combustion, but it is an example of an oxidation-reduction reaction. The oxygen is being reduced and the carbon is being oxidized in these cases. Let's see if there's some more examples of oxidation reduction. Yeah, there's another one. Again, a metal reacting with silver nitrate. That's very similar to the zinc one. That's oxidation and reduction. You can come back and look at this. Here's your metal, and it's going to a +2 ion, just like the zinc. Here's the reaction we started out with this morning, or when I started talking about reactions. Sodium plus chlorine forming sodium chloride. That's an oxidation reduction. We got an element here. We got another element here. They have the charge of 0. And we're going to, the sodium is going from 0 to +1. The chlorine is going from 0 to -1. So the chlorine's number is going down, it's being reduced. The sodium number is going up, it's being oxidized. There are some better examples. Here's silver or copper reacting with silver nitrate. And so this blue solution right here is copper. Copper ions floating around in there. You start out with clear silver nitrate right here. Clear and colorless. And then what are you getting? You put this copper tube down in there. It turns black. That's silver metal forming on it. And the solution turns blue. That's copper ions going into the solution. I was talking here about ionic equations. I'm going to talk about this now under this major category, precipitation. In the 1105 lab, which many of you are in, last week we mixed lead nitrate. I think I have a slide of this right now, with potassium iodide. This is colorless. And we reacted it, we got potassium nitrate. And does anybody remember what else we got and what you saw? This is experiment 6 in 1105. You mix these two test tubes together and yellow.
Something else.
You got a deep yellow precipitate. Potassium or lead iodide. The potassium iodide is soluble in water, but the lead iodide is not soluble in water. And you formed that, and it was heavy. If you let it sit there long enough, it just started falling to the bottom of the test tube. There was your lead iodide in the bottom of the test tube. This is a precipitation reaction. And to really, one of the key indicators for you is going to be right here. This means it's an aqueous solution. And what that is telling you is that lead nitrate is soluble in water. The lead nitrate has gone into solution. It's dissolved. It's uniformly distributed in the water. It's an aqueous solution. Likewise with the potassium iodide here. And likewise with the potassium nitrate. It doesn't precipitate. It's very soluble in water. But the lead iodide, we put an S after it, meaning it's solid. It's a solid, and it's not dissolving, and it's not uniformly distributed in the water. It's falling out to the bottom. It's all collecting in the bottom of the test tube. It's wet. Yeah, it's wet. It's around water, but it's not in the water. You see? That's what we mean. This is your precipitate. Just like when it rains. When it rains, the water is precipitating out of the atmosphere and falling to the ground. It was dissolved in, it was humidity, but the humidity is being converted into actual liquid water, and it's precipitating. That's why, you know, the weatherman will say, no precipitation today. He's not saying there's not going to be any lead iodide falling out of the sky. This is not going to be any rain, liquid rain falling out of the sky. But this is a precipitate in the chemical sense. Notice here, this is your indicator right there. Look for a couple things. Number one, make sure you don't see a really common acid and base on this side of the equation. You probably won't, because usually the salt being formed is in an acid-base reaction, is soluble in water. So you look at these and you can see I've got, and start trying to figure out the names of these. All right? Barium chloride, what's sodium sulfate, is forming barium sulfate and sodium chloride. That's soluble in water. That is not. There's your precipitate. So that's your, the main way you might see some questions on an exam for this module is it would say, which of the following reactions is an acid-base reaction? There'll be 5 reactions there. One of them will be an acid-base reaction. One of them will probably be a precipitation reaction. One of them might be an oxidation-reduction reaction. So you have to be able to pick out a acid-base reaction from among 5 reactions. Next question. Which of the following reactions is a precipitation reaction? So I'm trying to show you here how you might identify these. Now, I think, I don't know how I'm going to work out questions on this, but if I have some questions on the test on this particular part, like what is going to form a precipitate, you will have this table, this particular table right here. So let me explain the table, and then I'm going to look at another slide which is going to say which one of these would be a precipitate, and we're going to use this table to answer that question. Okay? So first of all, let's get our feet on the ground. What is this table showing you? So right here is the first major portion. These kinds of compounds are generally soluble in water. Which ones? So here's your first group right here. Here's your second group, your third group, and your fourth group up here. So what is this saying? Any compound containing the alkali metal, any salt of an alkali metal. What do we mean by that? Well, let's take sodium, sodium chloride, sodium nitrate, sodium sulfate, sodium anything, sodium iodide. What this is saying, if sodium is one of the ions in the compound, doesn't matter what the other ion is, it's soluble in water. Sodium salts are all soluble in water. Lithium, potassium, rubidium, cesium, and ammonium. So if I change those to ammonium chloride, ammonium nitrate, ammonium, now we're going to have to put this, sulfate. Any ammonium compound no matter what the anion is soluble in water. That's the very first rule or guideline right there. Nitrates. Okay, now they're looking at some negative ions. Any nitrate is soluble in water. That we saw just a minute ago. Lead nitrate was soluble in water. That actually makes lead nitrate more toxic than most lead forms because it will dissolve in water, which means it can be ingested easily. That makes it pretty bad. So any nitrate, any acetate, bicarbonate, chlorate, or perchlorate is soluble in water. So sodium nitrate, but even in an aluminum nitrate. Okay? We didn't say anything about aluminum yet, but it's saying any nitrate is soluble in water, so an aluminum nitrate is going to be soluble in water. You follow me? Halides. Any halide. So aluminum chloride, that's going to be a 3. Lead chloride, that's going to be a 2, etc. Any chloride is going to be soluble in water, and any sulfate. So that's a big chunk of stuff. There's a lot of stuff that's soluble in water. Excuse me. Halides. There are some exceptions. I'm sorry. That's what this other column tells you. So over here in the first 2 segments right there, no exceptions. There are no exceptions. You get down to the halides, there is an exception. Lead chloride or lead bromide or lead iodide is not soluble in water. That's an exception to this general guideline that halides are generally soluble in water, but not these. Oh, I put lead chloride here. I'm sorry. You see that? That's an exception. Sorry. I'm going too fast. And I've just unplugged. Okay, so there are some exceptions, and that's what that right side column means. Now when you go down to this portion, these things are generally not soluble, except, now look at carbonates. So calcium carbonate, magnesium carbonate, not really generally soluble in water. Most carbonates are not soluble in water, except if they are those carbonates. Sodium, potassium, rubidium, or ammonium. See that? These are the exceptions to this rule. Why? Because we said everything that's got a sodium on it, including carbonates. Okay? So I'll leave this chart up here. Let me get some of the scratchings off of here. I want you to be able to use the chart. There's some precipitates: cadmium sulfide, lead sulfide, nickel hydroxide. You see it's green. Aluminum hydroxide. All right, now let me write some of these down, and then I'll get that chart back. And what we're going to do is we're going to look at some of these and decide whether they are soluble in water or not. So I'm going to put here silver sulfate, and we're going to decide, are they soluble or insoluble? Calcium carbonate, sodium phosphate, barium hydroxide, sodium chloride, potassium carbonate, and magnesium sulfate. Okay? So that's our challenge. Here's our chart. And let me show you how this would be. We could have a situation like this. Let me get a simple one here. Yeah, let's take this one let's say we were going to react calcium nitrate plus sodium carbonate, and this is aqueous, and this is aqueous. And the question is going to be, is this soluble? In other words, we would put an AQ right here, or is this a precipitate, in which we would put an S right there? That would indicate precipitate. It's not saying it's soluble, it's saying it's solid. So we would be asking the question, if I mix this with this, would I get a precipitate? So let's take this first one, silver sulfate. That one is insoluble. So, okay, here's sulfates. Sulfates are soluble in water,
But not the ones with.
but not these. And this is one of these, right?
Yes.
That's the exception. So silver sulfate is not soluble. Not soluble. Good. That's how you use this chart. Now, calcium carbonate,
No.
not soluble.
Calcium.
Carbonates. Generally, carbonates are insoluble.
But it's with an alkaline minerals, isn't it?
But also that's an exception. The CA2 is also an exception.
This is an alkaline earth. That's alkaline earth. So alkali metal is group 1A. Has to be lithium, sodium, potassium, rubidium.
So are we going to have to memorize this chart?
No.
Yes.
No, you have the chart.
Okay.
No, you don't have to memorize this chart. I don't have the chart memorized. I'm gonna have a lot of it memorized. Obviously, I tripped over lead chloride here a minute ago. So I don't have it memorized. But yeah, if I ask you to do any of this, you will have the chart available. So this is not soluble. Sodium phosphate. Yes.
Yes.
It goes by rule number 1, and there's no exception. Soluble. Barium hydroxide. Hydroxides. Insoluble. Yeah, this is borderline. All right, that chart is saying it is soluble. It's not very soluble. It's not very soluble. So this one is a bogus one. I would say it's not soluble, but it's kind of borderline, has some solubility. Sodium chloride, soluble. Potassium carbonate, soluble. Rule number 1. Magnesium sulfate. Yes. Yes? Sulfates are soluble, and magnesium is not one of the exceptions to that rule, so it is soluble. Okay? So that slide, if you want to indicate those, that's how you use that chart. And I mean, another way would be like this. An interesting question would be like this. You could be given the question, you mix calcium nitrate with sodium carbonate and it might ask you to complete that reaction and predict whether a precipitate would form. And you would, now how are you going to complete that reaction? You're going to take this positive ion and associate it with that one. I'm going to get sodium nitrate. And it's going to be soluble. That's what the chart tells you. All sodiums are soluble. And then you take this ion and associate it with that ion. Double replacement reaction. And this is going to be a precipitate. Okay? So that's how you might finish some of these. What reaction didn't we get? We got precipitation. All right. Okay, I will load up Module 7 slides. I will also load up Module 7 homeworks and quizzes. If anyone did not get this, now most of this was due last Thursday, but there is a bunch of this due on Thursday this week. If anyone didn't get one of these, you're welcome to have one. I handed these out last Wednesday. Look, this is just a screen print of Canvas showing you the assignments. So go in on Canvas to your assignments. If anybody came in after I took attendance, let me know.
Do you have a sign-up sheet?
Oh, the sign-up sheet? Where is the sign-up sheet?
Number 11.
Christy? Right here? The sign-up sheet? Yeah, I got you, Kiki.